management system, as well as resource recovery systems. He was mainly responsible for the development of the LCA models East-West East-Tech at the Technical University of Denmark. Well, I may say that I know personally Dr. Damgaard. He's an excellent person, an excellent researcher. I'm glad for all the time we spent in Denmark back in 2010. And well, Anas, it's a real honor to have you here with us virtually, but we still feel your presence. And let us begin with your talk that's called Life Cycle Assessment of Waste Management. I leave you with Dr. Damgaard.
Perfect. Thank you so much, Carlos. I guess I'll just start sharing my screen.
Yes, please.
You should see. Do you see my big D2 logo now?
Yes, it's clear.
Perfect. Just move this. Okay, so thank you so much for the nice introduction. I was better at the English than the Spanish introduction here, and good morning all. As was already introduced, I'll talk about life cycle assessment of waste management. Before I start my talk, I would actually like to, and I just need to get a pointer, I'd like to give credit where credit is due to my colleagues, Thomas Christensen, Thomas Astrup, Valentina Bisinella, and Alessio Baldrin, because what I'll present now is something we have developed in our group within the last 20 years or so. So they have been a pivotal part of this. And of course, the most important is actually all the PhD students we've had in the group, because I don't know how many of you are PhD students, but at least in Denmark, that's where the real work is done, right? The rest of us, we just point in a direction, but that's where the work is done. So most of what you'll see as first authors are all PhD students that carried the big load here. So let's see. So just a quick outline. So first, I'll talk about give an introduction to waste and LCA, just to set the field. And then next, I'll talk about the learnings we've had from the last 20 years of waste and LCA. And then I'll talk about how we can use LCA and waste management both today and in the near future. And finally, I will come into a few perspectives on how do I see some of this going into the future. So if we talk about solid waste, this is not anything new. It was there even in early civilization, and waste is an important source also today for archaeological information, because this is one of the places where we find data about previous times, and especially right now, we can find a lot of information. If you go out and excavate an old landfill, you can find newspapers that are 50, 60 years old, and you can still read them in at least some parts of the world. The main reason we've started using LCA within the waste area is that we have problems, and I think the two big problems we have today is urbanization, meaning large material flows and large quantities of these wastes that are in the cities due to our consumption of goods and our production of the same goods, which we have to do something about. And then, of course, also the industrialization, where we get more and more complex products containing problematic chemicals and compounds that might make use of them problematic in the next step. When we talk about waste, it's important to be aware what is it we talk about, and the problem is actually there's no universally accepted definition. Each country or region, they often have their own definition, but a useful definition could be something like a leftover, redundant product or material of a no or marginal value for the owner, and which the owner wants to discard. And already here we can hear this is from the view of the person who discards it, but of course it's important to be aware that doesn't necessarily mean the material doesn't have a value. It just doesn't have a value for whoever discards this material. It also suggests these four things that are important with regards to waste, that there is a link to to the time. And this is because new products, war shortage, unfortunately, as we see right now, can have quite big impacts on which products we use and how much we use of these materials. The same with regards to location. Are we in a rural or small town versus a dense urban center? We will have differences in generation type. We will also have climatic differences. It's probably still a lot hotter in Mexico than it is here in Denmark, where it's just around 0. Culturally, there will be differences. Food-wise, what is it we eat? What is it we consume will depend on different cultures. And finally, social conditions. Are we in a more affluent area, or are we in a poor area of the city? Well, again, that will depend on different patterns. And all of this is something that's important, because when we talk about waste, it seems like it's this homogeneous material, but it is really these very heterogeneous sources where one solution doesn't always fit the bill. When we think about waste as a non-researcher, most people don't think about waste in their daily life. They first think about waste when it looks like this, and this is when waste management collapses and waste is not collected. Here are some pictures from Naples in Italy, but I can tell you we can also do the same in Copenhagen when we have the collection workers strike. People suddenly start talking about waste, because after a short period, of course, smells, etc., starts impacting it. But there are really 3 issues that govern why we need to have strategies for managing waste. One is, of course, economy. The scale of this problem makes economy an important issue. In a Danish context, I can say it's somewhere between 0.1 to 1% of the GDP, depending on how much we include in this. Of course, 1% doesn't sound like a lot, but we have to remember that the economy covers a lot of sectors, and this sector is actually quite small. The other one is the contamination of the environment, and that's closest to my focus area of research, which is this, that waste components will transfer impacts to air, water, soil, etc. And of course, that can give us quite big issues with with both our own health, but also the environmental health. And finally, we have resource issues, because waste contains resources, and if we don't manage to recover it, well, then we lose these resources, and more we consume too many resources, and therefore we are going to get closer and closer to a place where we don't have the resources we need when we need it, and especially the next generations. So to combat this, more and more, we have started using life cycle assessment. And I'm just going to give a very brief fly-in to what is life cycle assessment, for those that don't know it. It's a holistic approach for environmental assessment of industrial products. It was introduced really in the 1990s. Historically, you can probably go further back, but that was when it really started to get the shape it has today. And some of the classic examples were comparisons of alternative containers to beverages. What should we have it? I think one of the very first in Denmark, at least, was on milk. Should it be glass or cartons at this point? And it's been where it grew from. It's what we call like cradle to gate. So we start from raw material extraction via processing those materials into semi-products that goes into final products. We distribute these, we use them in society, and then we maintain them, and finally we dispose of them in the waste. And some of the early LCAs, they really, back when I was a graduate student, LCAs ended in solid waste, and it would be X kilo of solid waste to landfill, or X kilo of hazardous waste to landfill, or X kilo of waste to an incineration. And that was sort of our knowledge about what is the impact of this. The main focus was more about what are the exchanges and emissions from this whole view you see here, meaning what are going in and what is going out. both with regards to the use of materials, energy, etc., and also what emissions are coming out from such a system. And of course, the assessment, we say the life cycle because it's the full life cycle, but it's really not a cycle. When this started, it was a linear system that ended in this disposal. The impact assessment is then where we take all these inventory and knowledge about emissions, and we convert them into potential impacts to the environment. When we talk about LCA and waste management, this was something that started in, I want to say, the late 1990s. Some of the early places that was done were Sweden, the UK, and the US that developed their own models for doing this. In 2020, we did a tally, and by then we could see that there were at least 400 scientific papers that have been published around the world looking into LCA of waste. And waste LCA really differs from product LCA in that the complexity of the system. So if we look at this, what we see is that where before we had this very linear system, it doesn't look the same when we look at it from a waste perspective. And that's because our starting point is a waste material. And as I said earlier, waste is heterogeneous, meaning it can consist of many things. How much plastic, how much glass, how much metal, etc., can have a huge impact in what we want to do with it. And that also means that source separation becomes very important. And this is where it becomes hard, because normally in technical system, well, I mean, we can plan our way out of it, but in source separation, especially when it's waste, often there's users that can either be the citizens or it can be workers in industry that has to be informed well enough to do it and want to spend the time on doing this. We have a system where we have treatment. We can have multiple outputs from these treatment system. So that could be a landfill where we both have leachate, we have gas, etc., which we have to take care of. We might have return loops in the system. Could be wastewater treatment where we have a sludge coming out and we have some water when we dewater the sludge that will go back into the system. And we have a disposal phase that is also very complex. Finally, we have the things that emissions depend on the composition of the input. So it's not just we can say we made one LCA and then we have the results, because if we start changing the composition of the material going in, we need to make sure that we update along this whole value chain, because, for instance, if I put a brick into a furnace, the brick will not melt, but if I put plastic into a furnace, the plastic will combust and be converted into air emissions. So there is a lot of complexity in understanding all these things. And then, of course, the benefit downstream should be we get some avoided energy and materials out of this. Similarly to the normal LCA, we will convert all of this into emissions, into impacts for the other LCAs. And to do this, it's important to have a quite sort of stringent look to it. So I'm coming from a technical university, so we have always a sort of engineering approach to it. So what we say is that any LCA really needs to have beneath it a really good MFA that allows it, and material flow assessment that allow us to understand where is things flowing in such a system. So if we have a material coming into a process, we also know we have to put some materials into the same process. We know that there will be emissions both to the atmosphere, probably also to water, maybe to soil. And we will have materials coming out from such a process. Maybe they're recyclable, maybe they don't have a value, maybe it's a compost we can use on land. So really, we need to understand what happens with materials as they progress through these systems. And just to give an example on this, I will do on the next slide, but the benefit of this is that by having this mass approach, all generated waste and the residues are kept track of. And that means nothing is forgotten. So we make sure to have a systematic way of doing this. And this is what the LCA models can help us keep track of, because it's a lot of data But this is where we have developed models that can help us do this. And here we both have models from our product LCA type of studies, but then there has also been models developed more for the waste regime. The goal should be that all emissions can be identified by evaluating the discharges from the system, both the intended and the unintended. I'm just going to give a very simple case here where we have some waste being generated here. And then we can make a mass balance first, where we say, okay, we have some paper going to a paper sorting facility. We have some waste going straight to a landfill. And then we have some waste going to a composting, some bio waste. From the paper MRF, we will have paper and cardboard being sorted out that then in this case will be sent on to recycling purposes. But we will also have some impurities that will have to go to the same landfill. In the landfill, we will actually have the buildup of stock. That's why when we see landfills in the areas, we see these mountains of trash that at some point then will be covered by soil, maybe vegetation. So we have a delta change to such a landfill, and then we have gas being generated. And there, of course, how we manage the landfill will be important, because do we capture this gas or do we just emit it to the atmosphere? Same for the composting. We have a composting. We have some residues from that, again, that will go to the landfill. We have a finished mature compost coming out, which we could apply to land, agricultural land, parks, etc. And then we have a lot of emissions coming out. So in this case, we again also lose a lot to the atmosphere. Of course, the importance is what happens with these emissions, because as I said, methane, we are aware, CO2, both of them are greenhouse gases, but especially the methane is problematic because it has such a high impact. And especially in the waste area, it's the methane that is the big issue. And the issue is we can manage it if we can control it well enough, then we can convert it into CO2, use it as fuel and convert it into CO2. So after we have done the mass balance, we can do the same from an energy budget, and we can go in, and I'm not going to go through all the numbers, but we can then look at how much energy does it take to run this whole facility, and what do we get out in terms of energy budgets, in terms of recovered materials, etc., that can be used as an energy carrier. And we do that, and then we can do the same with emissions, and we can put emissions on both the direct emissions and then also the savings of the emissions downstream. And this is really where we get into the LCA part of it, but this is layer on layer on layer, where we start by understanding the flows, then we start understanding what goes in and out of the system, energy, materials, and finally we can then put on a layer where we understand the emissions. So this is sort of the steps we have in any LCA, which is needed to get this conceptual understanding. And by doing it in this stringent way, we get a much better understanding of our models. In a waste model, of course, we don't have one process, we have multiple processes. And one of the things working with waste that's actually not that funny always for the industry is that anything the waste management industry does is an impact. It's a load to the environment. They use a lot of material and energy, and they have emissions to the environment. But by doing better waste management, of course, what we can do is downstream, we can recover materials and energy, and that can lead to avoided production of materials and energy, which in this form will be a type of savings. And of course, the goal here should always be that the loads to the environment should be smaller, preferably much smaller than the savings. So we get a net saving by doing this. So we get more benefits than we get direct impacts. Sometimes maybe when I use these words later, I'll talk about the direct operation. We'll talk about indirect upstream impacts that are needed to run such a system. And then we have the indirect downstream impacts to such a system. And this is where the indirect downstream is, of course, somewhere out in society. This happens because this is where we might need less of something produced. To talk a bit about, okay, but what has LCA done for us? Together with colleagues a few years ago, we actually went back and did a review of what has happened in the last 20 years, and what are the learnings from all the LCAs we have seen being carried out in this period. And we could, of course, have gone back into the 90s, but we focused on this millennium because this is where most of the work has been done. From that, we grouped it into 6 things I'll talk more about in detail now. One is the importance of system thinking. One is about detailed technological data. The understanding of what does time horizons mean when we start talking about waste management and in life cycle assessment. What is recycling, especially in an LCA? What is the importance of exchanges with the surrounding energy system, because this plays a very big role? And what is the importance of the waste composition itself? And if we look at it, then the professional discussion in the 70s, 80s, and maybe early 90s, they were very focused on technologies, but on a rather simplified level understanding. What was best? Would it landfill, incineration, composting? And I mean, I'm too young to have been in the field, but what we heard from some of the older professors was back then, waste management were more focused by practitioners, businessmen, and much less so by scientists that were looking at it more systematically. Environmental arguments were used, but often without much quantification. So landfill bad, incineration good, incineration bad, recycling good. And there was very little focus on the different waste types. The fact that some technologies might work better for some things than others. And the fact that we would always have residues, that whatever we do, even the best recycling operation, we will have something that we need to do something else with at the end. And there was actually very little understanding of the flows, what happened with the different inputs, where did they go in these different systems, and where was it really the loads and the benefits was in waste management. So with this, it was LCA started to come in, and the thing with an LCA is it has a clear goal and scope. It has a clear functional unit. What are we looking for? And it has a clear reference flows. What is the total quantity we look at? And here in the early zeros, this was also where in the European Union, we actually got it into our waste framework directive that waste could be used, waste LCA could be used to sort of move up and down in what we call the waste hierarchy, meaning we could use arguments for why would it, for some cases, be better to burn something than recycle something. And that could be by through an LCA showing that actually it would be better for the environment by burning a low quality recyclable material than trying to recycle it. Another thing was this, that all engineering within waste management demands data for all technologies. So I showed this just before. We need mass balances, energy budget, emissions account. And we realized when we started doing the LCAs that often we did not have such data in any consistent way. And this really forced us to start improving our data collection on waste, on the technologies and exchanges. And I would say in my own PhD and the early years of my research career, most of the time actually was not spent on doing advanced LCA methodology. It was to figure out what was the flow of materials in and out of different technology operations, going out, measuring it. What were the components and compounds we would have released? What were all the processes? And all of this should lead us to understand, okay, get this inventory of emissions for our system. And this was especially where we started to understand that water content is crucial in these things, because going from different sort of area to area, you would have very, very different water content in the material you look like. And since the water, it only carries its weight and it actually removes some of the energy, it can skew the results to a very high degree. So technology data was actually some of what we could see was very needed. Another thing was that LCA really demands 3 time horizons. There is the time horizon for which the LCA is valid. So this is often 30 years. And why is it 30 years? Because that's probably the lifetime of a building that we extract, construct to take care of our waste. So that's how long we will depreciate the investment in such material. But then there's also the time horizon of the emissions from the system. This is where we look at different sort of impact categories will have different sort of time horizons. So this is where, for instance, when we talk climate, we often have this 100-year time perspective, but which is where actually a lot of us says we probably should have a much shorter time perspective, because if we make decisions for how a technology will look in 100 years, we might actually worsen the impact in the short duration, because in that case, methane, for instance, will be much less important. And in a time where speed and implementation must go very fast to mitigate some of the issues, then what time we are looking at is very important. And this is actually where most LCAs have used this 100-year time horizon and very long time horizons for systems where we probably need to have much shorter. This should also remind us that there might be changes during this time horizon. So in these 30 years where the facility will be there, will the waste input be there? Will that change? So we had that case in the city of Copenhagen where we built a big new waste to energy plant, and a lot of engineers had already before then said, well, I don't think you will have enough waste because we started recycling more and more material. And today we have to import a lot of waste from other countries because we simply do not have enough waste to burn in this. And this is where the waste input, of course, the amount, but also the composition changed. In the same period, we've started getting a lot more plastics. That means we have a lot of more fossil CO2 outputs coming from this. So again, time when we make this, we have to reflect of these changes. Also, the value of exchanges over the boundaries. Is the material worth the same? And I'll get back to that later, as it is now. And then especially if we talk landfills and ash disposal, it's important to consider that gas and leachate amounts and the quality, they will change a lot over time. We'll have a lot of gas in the early phase, and then it will slowly taper down as more and more of the material have been converted. And that, of course, means that if we just assume a linear or a constant amount of gas production, we will overestimate the impact in the late stages and underestimate the early stages. So this is where it's important to actually understand what's going on in our landfills and can we capture this. As an example, very often we hear that landfills can capture something like 90% of the methane being generated. And that is actually true. If we talk about the capture rate after we have finished the landfill and put a cap on it, at that point, we have very good control of what goes on in the landfill. And at that point, we can capture 90%. The problem is just that a vast amount of the gas is being produced in the early phase before we can cap the landfill. And that means we lose a lot of this gas. So when we talk about time, it's very important to be aware of where are we in this time period and how good are our technologies. Of course, technologies will also evolve. So what is the best might not be the same now and in the future. How much carbon is in the landfill after 100 years, carbon will be stored. But at the same time, we also know that there will be toxicity left in such a landfills for much longer than 100 years because we put it in there and it's quite stable, for instance, the heavy metals. And finally, one of the impacts that are quite poorly actually measured today is what happens with the leachate in the groundwater. If the groundwater is a source, or it ends in a freshwater basin, which is not captured in a lot of LCA methodologies today. So LCA here reminder us that there's a lot of lack of data on what actually happens in these long time horizons, and we might need these better methods for incomplete coverage of, for instance, what happens when we contaminate a groundwater source. When we talk about recycling, what LCA has taught us is this, that of course waste management is a load, as I said before, but the benefit comes when the materials, energy, and nutrients we recover and deliver to society, they avoid the production of other materials. And this is where it's important to really start looking into what is it we produce when we do recycling. A lot of the early LCAs, they were very focused on material recycled, avoid good. But this is where we started saying composting is not really recycling. It might be seen as recycling, but it's really only in the case where the compost can act as a recyclable product and substitute for other soil amendments that we can say there is a credit for doing this. And this is because often we actually have a lot of low quality composting facilities where the materials will not substitute anything. They might end up as a soil cover on a landfill. Another one is material recycling, which is something that is heavily discussed in the European Union right now. And this is because quality really matters for what is substituted, and lower quality, the less valuable of a substitution. And this is really because, I mean, just because we recycle something doesn't mean it will avoid a production of a new material, because if it can't replace material already in use, we don't get the same quality. And this is where we have to remove just that downcycling, meaning going to a lower quality product is not really the same as recycling. It should be considered downcycling, and we need to figure out, is there a need for the material that we are downcycling it into? This, of course, means that we extend the responsibility of the waste management beyond the waste management's own business, because they actually have to start acting and making sure this happened. In the EU, this is then also meaning we are moving upstream now, because now we get the extended producer responsibility schemes, which is really saying if a company puts a material out on the market, they need to make sure that there are operations that can recycle these materials back or recover the materials at least at a decent way. And this is something where LCA has definitely pushed for this. Of course, here we also relied on external databases that we can use and to follow the value chain to understand where is it these materials go. We also need to understand the exchange with the energy system, because LCA has taught us that the waste at least in a Western world, contains a lot of energy, and this can be utilized. But the benefit really, again, depends on what is it we substitute. We have different values for electricity, heat, and fuel that is dependent on geographical, local conditions, and the benefits will change over the years, especially right now as the energy sector is moving into a more green direction. So if we have sort of different energy profile here, and this is actually from a result you will see later. So here we have different energy mixes we could have in this. Up here in the top is for electricity, where percent of different fuels over here. And then down here we can see, okay, but what is then the climate impact of delivering 1 kilowatt hour of electricity? And we can see, of course, can be quite high if it's pure natural gas we put in. But if we move to pure, almost only wind or solar, and even these combined effects here in ES3, which is quite close to the Danish mix right now, we see we are at much lower values. This is, of course, good from a sort of energy system perspective. It means that when we use electricity, we have less impact. but it also means if I start producing more electricity, I get less benefit out of that, because the alternative way might actually be less impactful to the environment. And again, here it's of course we're dependent on then external databases that can tell us to our LCAs, okay, how will the energy system change in the future? What are the dynamics of these values for the substitution? And this is where I know in most places in the world, the authorities are developing strategies for how will the energy system look, where in the Danish case, already by 2030, we expect to have most of the fossil fuel out of the system. Finally, we have this with understanding the waste composition, and this is really where LCA has taught us that environmental impact of waste management really depends on what is the waste composition, which means that not all technologies are equally suited for all waste compositions. And as an example for this is that Asian waste is less suited for incineration. And this is because if you're in a context like Denmark, if I have residual wastes, that waste have an energy content on 10 to 12 megajoules per kilo of wet weight, where in Asia, that would probably be somewhere 3 to 4 megajoules per kilogram of wet weight. And that can actually mean you might not be able to burn it without adding other types of waste that can increase that energy content. And this is where I think we see LCAs being used from one area, region, or country to inform decision making in other areas or countries where the conditions are very, very different and where you don't get these impacts. And this is why local waste composition data should always be used, and why a lot of our LCAs, the very first step was actually going out and sorting materials to get an understanding about what is the composition of these materials. And this is, of course, also then where it's important that the LCA, that we can do waste composition specific results, so that when we change the composition, that our results change. So that was sort of 6 of the learnings that we took with us. But then the question was, okay, but how can we then use LCA today and in the near future based on this? And the first question, of course, do we still need to perform LCA and waste management, or do we need enough now? And we found that the answer is that there are 6 application areas where we think LCA still is useful. It's about understanding existing waste management systems. It's about improving them. It's about comparing technology performance. It's about developing technologies, prospective technologies. It's about policy development, strategic development, and finally, it's about reporting. What is the impact of this? So if we take the first one, understanding an existing system, this is really extremely important, and especially if you're moving into the field, this is probably going to be your first one, because there's so much we can learn by doing an LCA of a system. What are the main flows? Where are the main environmental loads and the main savings? And this first example, this is actually from back when I was doing my PhD, where I collaborated with some Chinese people, where Yan Chao here is actually a professor now in China I'm still collaborating with, who was a PhD student back then. And what we did there was actually go out, gather data, and start to understand, okay, when we take a snapshot of Hangzhou in this year, where is the impacts and where is the benefits? And then we assess that for different environmental impacts. I would say this was quite crude, elementary from how we would do it today. But back then, of course, we were dependent on software that was a bit more limited than what we can do today. But it gave us an understanding, okay, there is something we need to do with the landfill. There is benefits from material recycling already in these systems. And then there is something with their incineration, at least if we're looking at global warming. So using this to understand this is, of course, the first step. And the next step is then, of course, to say, based on this, can we then improve our existing waste management system? And this is where we can use it to assess what will be the impact for potential improvements prior to decision making. This is an example from Irkutsk in Russia, where we work together with the city and one of the researchers there. And scenario 0 here, this is climate change impacts I focused in on here. And out here we have the person equivalent, which is a metric in LCA to say how many average persons does this correspond to. And the yellow here, that was their landfill at this point. And then what we said is, what is the benefit if we divert materials away from this landfills? And then we have various scenarios, and I'm not going to bother you with going through them. But actually, I think one of the interesting things for the city itself was just by moving from the open dump, which was the type of landfill they were using there, to an engineered landfill, which is this scenario 1, we would go from having huge impact to the environment to actually having a much more contained, and we actually would start seeing sequestration of carbon being so high that we could have net savings through such a landfill. And why am I saying that? Well, because I think it was not realistic when we worked with Russia at this point that they could do these much more advanced strategies. But just telling them that actually for not much money, you could actually make a big deal by just closing down the existing landfill and building a modern landfill, which could be operated much more. So this is where we can start looking at these improvement potential. And then often when this type of studies are done, we can then also look at what is the benefits cost-wise. We can also compare different alternative technologies. In this case, we actually looked at different reprocessing technologies in Sweden, and we looked at the same reprocessing of waste paper would actually have quite big variation. And then we could use that to go in and say, okay, but why is it in these factories they have much higher impacts in these factories? And then we could use it to optimize the way we consume energy, etc. So one of the differences here was that some of them used a lot of more bioenergy, where a lot of them used a lot more electricity that at this point of time in Sweden was very fossil based. So this type of assessment can still be done by basically going out and benchmarking different industries, similar industries, to figure out which are best performing. We can also do that in technology development with new and prospective technologies. And I think this is actually one of the most important areas to do it. And this one is a development of waste electrical and electronic treatment, where they were trying to develop a new technology where instead of using the normal pyrometallurgic system, they would use a bioleaching system that should be better for the environment. At least that's was the thought. But what they found was actually that with the current system they could develop, that actually the impact was much higher for a lot of these systems, and at the level it was definitely not mature enough to compete with the existing full-scale technologies. And this is, I think, where it becomes very important, especially if you're a decision maker, that you actually ask the people who come with a new technology to provide evidence that this is actually better than status quo. Just because we put bio into the name doesn't necessarily mean that it's better for the environment. And finally, we can use it for policy development, strategic development. So this is another case from two of my colleagues. This is a follow-up on some work we did on carbon capture, where at the Danish, one of the incineration plants, we are running tests with carbon capture of the CO2. But then the question is, should we utilize it or should we store the carbon? And actually, based on this result right now, the main focus would be to say, in this case, we should probably store it, because what these results here show is the line here, that's the baseline of the facility today, operated as it is. And then we have these different options, different options. And it really says that we need to have quite clean energies, and this is ranges when we have So unless we can move to these cleaner energy scenarios, we are really not gonna be able to operate and utilize this well enough to be able to say that this is green. And this is a big issue in Denmark, at least right now, because we are doing this green transition, and we are making all these new technologies that require electricity. And right now we actually introduce new technologies that require electricity faster than that we can expand the electricity production. And that means that we are actually keeping the fossil energy infrastructure in, because we don't make sure that it's a bit the chicken and the egg. We need to make sure we have the green electricity before we start using the green electricity. And this is where this type of LCA can inform the decision makers. Yes, this is a great technology, but if you want to do this, you first have to make sure we expand the energy infrastructure before we can do this. And finally, we can use it for reporting. And this is an example from a wastewater treatment plant, where we went in and we looked at the reporting over time. And the goal there for them was to say they wanted to be carbon neutral, but of course to become that, they have to control their emissions a lot. And what we found was that actually for this facility, this is the net impact over time. And what we saw was that even with all the things they're doing, with trying to recover more and more energy, the net zero, they're nearing it, but they actually can't get below it. And what we said is it's probably more important to make sure to start also focusing more on controlling their emissions, instead of just focusing on how many resources and energy can they get out of their operation. And I think this is important in the decision context. So in the future, what are the challenges? Some of the challenges when we talk about LCA is that energy will be more green, and products therefore also more green. And I think this will change the value of these exchanges over the boundaries. And that means that energy and coming out and product coming out might not have the same value as they have right now. So it's important we have this temporal consideration. The same is the linear economy, at least in Europe. What we're seeing is it will weaken. We are starting to see more circulation. This means that the value of the recyclables will substitute less virgin material and more recycled material. That again means the value of doing this might not be as high from an environmental point, but of course that should also mean we already have converted our system into a more recycled material. We will have different materials in use. That might mean that the technologies we have now are not there to take care of the materials that are coming. This is one of the big issues right now, is we introduce new materials faster than we can make technologies that can make sure to recycle them back into the loop. So this is where we need to make sure we design for a circular. We have different shopping patterns. We'll have different items, different ways of shopping, which means we will have different waste composition, more and more e-commerce, meaning more and more cardboard. And we will have different food patterns, which means that the type of food waste will also start to change. For waste management, that of course, as I said, we will have different waste composition, we will have different technology focus on what we should do, and it will give us an uncertainty in what is the value actually when we recover these materials. And therefore, LCAs can provide overview or a range of potential scenarios and handle the uncertainty associated with this in a waste composition, the new technologies and the new substitutional value. So I definitely think there's gonna be a need, and probably even a bigger need in the future, for doing LCAs, because we move into this very, very uncertain time where we do it. So we need to be clear on which methods we do, but we need to be able to handle the uncertainty. And then I think that the most important part is actually we need to be transparent in what have we done, what data did we use, and what results was we going into. And I don't know with time. See if I can do this quick. This is something I've discussed with Thomas Kristen a lot, and one of them is a post-fossil utopia. So if we are in a society where all our energy is based on renewable energy with a low impact, this means that the use of biomass will probably also be restricted, because we will need biomass for fuel, feed, timber, nature conservation, etc. That also means that carbon starts to actually be a key element in our society, because we will have reduced fossil carbon available, and therefore we still need carbon for fuels, plastic, etc. Since waste contains carbon, and this can be captured via carbon capture, which is what's evolving right now, and it can be converted into fuels or baseline chemicals. This is where a lot of the research is right now. This really means we think that in the future, waste incineration could be a good place to start with, especially if we couple it with producing the hydrogen for the fuels and chemicals, because we need hydrogen for that. And that's because when we produce hydrogen, we will get oxygen and we will get heat as some byproduct. And that means that we can take the oxygen and put it into the furnace. That will give us less flue gases produced, because now we have less other gases going in, so it will just be the pure combustion. And it also means we have the heat, and if we have a waste to energy plant where in Denmark we have district heating next to it, well, then we can use the heat very efficiently. This of course means that we have to develop new technologies that can handle these things. We need to have new ways of using our energy, but this is where we really have to remember when we do the LCAs. One thing is how the system looks right now, but we probably more and more needs to look out and guess how could the future look, and how would we develop technologies that can handle that future. So we think this leads to a great opportunity. So just to round up with this, LCA has given us a lot of data on waste management. It has enhanced our understanding of the system and has taught us where the environmental loads and benefits are. There's still a need to do, and I talked about that, from understanding all the way down to making decisions on basis of this. And then considering all the dramatic changes we're seeing these years in the energy sector and how we produce products in our carbon, and eventually in the waste, there will be a lot of need for LCAs as I see it in the future. But it's in scenarios, it's in a future where we'll have a lot of uncertainty in the foreground and the background system on what's going to go on. I think therefore it's very important that we test all the potential pathways that society can take and figure out what are the most robust technologies that can fit into this change. And with that, I will just say we are focused on getting quantitative results. I think in the future, we need to focus on identifying pathways and being less focused on what is the specific result, and more have some of these future pathways, sort of directions, and see, do we think that's a robust way to go? And with that, I'll say thank you.
Thank you very much, Anas. It's been quite a very interesting presentation with a lot of background and prospective information. I see many questions in the chat, so I will give the word to my co-host, that is candidate Dr. Alonso. Are you there? So you may pick
yes,
some of the questions. Yeah.
Well, first, I would like to personally thank Professor Anders for this very interesting presentation. I can be sure that the life cycle thinking is or should be a very important part of our research. Here in the chat, we have a few questions for you, Professor. The first one from Gael Aranda. The question is, good morning. have you worked with the co-processing of waste to create alternative fuels? I read that some cement industries use it as a fuel for their rotative ovens.
Yes, yes, we have worked with that, and I would say, especially in the cement industry, it is definitely what they do. They use a lot of waste. We do it in Denmark, and as far as I know, for Mexico, it's actually in your national determined plans for the IPCC is actually to take some of the waste in that direction. Of course, this is fine in a transition period where you could say the waste can replace coal. That would probably be the alternative fuel going in, but we should remember it will still give a lot of fossil impacts. I think in the cement industry, what I see in Europe is they are starting to focus to more say, can they get their hands on biogas and run it in that direction with fuels from bio waste, because that could be a way to move in a more green direction for this.
Okay, very good. I think we still have time for one question. Here is another from Maria Guadalupe Salinas, and her question is, well, first, thanks for your excellent talk. The question is, what do you think are the main challenges for applying life cycle assessment in developing countries like Mexico? Thanks.
That's a great question. I think one of the big challenges is data. As I said, we have spent, I think, our group, we probably had within these 20 years, we've had, and I was one of them in the early phase, we've had probably 40 PhDs internally. We've had a lot of external people coming by like Carlos. And I think of those, 35 of them have, to a big part of their PhD, focused on gathering data. Because to be able to model, we really need to do it based on good data. And I think especially for some of the technologies in Mexico, it's important that you get local data, so local energy data, local landfill impacts, local efficiencies in the industry, etc. So I think a good starting place is going out and getting some of these data. I think a lot of the methods and approaches in LCA, they are more universal, but the data is very regional, and that's what really makes the big difference between just a standard model and an actual very good replication of the real world.
Okay. Doctor Carlos, ¿cómo vamos con el tiempo? Procedemos a...
Sí, ya finalizamos, ya son las 11. ¿Das el reconocimiento?
Sí.
Continúa.
Ok. Me comenta si... ¿Se veía mi pantalla? Perdón. Okay. We would like to give this certificate to Dr. Anders Damgaard, who participated as workshop speaker with his talk, Life Cycle Assessment of Waste Management in the Simposio Ambiente y Bioenergía 2022. Thanks, Professor, for this great talk, and well, from the part of all the members, a great thanks.